to 100. So on this problem here, you have a pole. It goes from point O to A. Then you have three cables which are attached to the pole at point A, and you get three forces. Means you have a force Fp, then you have a force Fc, and then you have a force Fd. Then you're also given some length here. For example, you have this length here, which is 10 meters. Then you have another length here, just the height of the pole as 24 meters. Then you also know the coordinate of the peg at C. This length was 18 meters. Then you have this length, which was 16 meters. Then there's another peg here, which is at D. Then you know the length here as 12 meters. Then there's another length here, and that's 8 meters. And the question here is to determine the magnitude of the resultant force Fr and its direction. So we're looking for the force Fr, which is the resultant force, and it's going to be the sum of the force vector Fb plus the force vector Fc plus the force vector Fd. So that's the state equation where you have three forces acting at the same point, and all you are doing is just adding those three force vectors, and that should give you the resultant. And once you have the resultant vector, then you have another set of equations that allow you to find the magnitude and the direction. So the whole problem boils down to basically writing these forces in vector form. So if I look at, let's say, force Fp, then we need to know what kind of information we have for this force Fp. Now we know its magnitude. The magnitude was given as this one here is 520 Newton. Same thing as Fc. The magnitude for that is 680 Newton. Then we have the magnitude for this as 515 Newton. So if I go back to the force Fp, then we know its magnitude, then we should also be able to find the coordinate of this point as well as coordinate of point at Z, which is P, and so we know all the lengths. So since you know all the lengths, it's possible to find the coordinates for that 2 points. So if we look at the coordinates of point A as well as coordinate of point B and coordinates of point C and coordinates of point C, those should be possible to get, and if we know that, then this force Fp will be equal to its magnitude multiplied by a unit vector which goes from point A to B. Same way, your force Fc will be the force magnitude multiplied by a unit vector going from point A to B. Same way, your force Ft will be the force magnitude and a unit vector going from point A to B. Then we can go and a step further, and I can say that Fp really is the magnitude, then the unit vector will be a vector from A to B divided by its own magnitude. Then with this thing here will be the force magnitude, and then force the vector AC divided by its own magnitude. Same thing going to be true here. So you have Ft, and you're going to go from AD and divide by its magnitude. That's going to be AD. So those are straight equations, and now we need to find the vector AB. And to do that, we need the coordinates. So we go back to the point. Like if I look at the point A, this point is on the z-axis at a height of 24 meters. So the x-coordinate should be 0, the y-coordinate should be 0, and you should have 24 as the z-coordinate. Then when I look at the point B, then it's in the along the y-axis. So being along the y-axis, the x-coordinate should go to 0 and the z-coordinate should go to 0. The only thing which is non-zero is the y-coordinate, and the point is on the negative y direction. So the y-coordinate becomes negative 10. Then we look at the point C, and that point happened to be on x, o, y plane. So since it's on the plane, your z coordinate will go to 0, and then from here if you drop a perpendicular on the y-axis, and this distance should give you the x coordinate, so that's 16 in this case, and then this distance here, that should give you the y coordinate, and that happened to be 18. That's for the C. Now we need the same thing for D. Now if I look at D, the point still is in x, o, y plane. So being on the x, o, y plane, your z coordinate automatically goes to 0. Then for the x coordinate, the distance is about 12 meters, except it's in a negative x direction. So you're going to take negative 12 for the x coordinate, and then the 8, which is along the y-axis, that should give you the y coordinate. So that's pretty much all the coordinates you need to work with this problem. Now, if I need, if the force magnitude was known, it was 520. We need the vector AB. So, what you're going to do is, you're going to take the coordinates of B and you subtract the coordinates of A, because P is going to be, the vector goes like this, and that's the tip or the starting at any point of the vector, and A is the starting point of the vector. So let me see if we get 0, -10, and a 0. So these are the coordinates of point D. Then for the x A, you have a 0, then we have another 0, and then we have 24. So that's the coordinate of point A. Then you subtract these numbers, multiply that by I, you subtract this, multiply it by J, you subtract this, and you multiply it by K. So this whole thing, all the way up to here, is the position vector AB. Then its components. X component is 0, Y component is 10, and the Z component is -24. Therefore, its length would simply be, you take the x, which is 0 square, you take -10 square of that, plus -24, and the square of that. So that's what represents your vector FB. Then you're going to do the same thing for C. So the magnitude is 680. We need the position vector AC. Now to find AC, you're going to look at the coordinates of C first, because C is the tip. So I could write 16, I could write 18, and a 0. So those are the coordinates of point C. Then you write the coordinates of A. You have a 0, then you have another 0, and you have 24. Then you subtract these, you multiply those by unit vectors I, J, and K. So this whole thing now is your vector AC, the position vector of point A with respect to the point C. Then we look at the components. This component is going to be 16. This component here is going to be 18, and this component here is -24. Which means if I take the square root of this, you have 16 square, then you have 18 square, then you have -24 square. And the bottom part here is the length of that vector. Then we're going to do the same thing for the third one. We're looking at the magnitude as 560. This time we're going to take the coordinates of point D. So you're looking at -12, 8, and a 0. A is the same, so you go 0, 0, 24. Subtract this, subtract this, subtract this, and then multiply this by unit vector, another unit vector, and another unit vector. So what you got now is the position vector AC. Then you need its length. You go square root. The component here is -12. The component here is 8. The component here is -24. So the length will be negative 12 square, then you have 8 square, negative 24 square. And that's the length of vector AD. So, you use the case 3 and you wrote all the force vectors. The rest of it is just calculations. And this length here, if you go through the actual calculations, it's going to come out to be 26. Same with this length here. If you go to the actual calculation, it's going to come out to be 34. Then this length by itself should come out to be 28. You just have to do the calculation. Then the force will be 520 times 0 over 26 times I plus 520 over 26 negative 10 times J plus 520 over 26 negative 24 times K. So that's your first force Fp. Then the second force. The second force will be the magnitude 680, the force coefficient is 16, divided by 34 times the phi. Then you go 680. Then we're looking at 18 over 34 times the j. Then you have another 680 divided by 34 times negative 24 times 10. Then we got a third one. Now you're going to have 560 divided by 28 negative 12 times of I. Then we got 560 divided by 28, and then you have 8 times the j plus 560 divided by 28 times 24 times 10. Just plain math on all these forces. So this is going to be equal to 0 times of I, and this is going to become negative, and you have 200 times the j, that's also negative, and that's going to be 480 times the 10. Then this one here should give you 320 I plus 360 j negative 480 k. Then the last one will be negative 240 of I plus 20 times, so 160 of j negative 480 of k. So this one is the force Fp, this one is the force Fp, and this one is the force Fp. So basically, after going through all this work, you managed to write each force in vector form. Then we go back to the very first equation I wrote, which means we're going to use this equation. We're going to add every force vector. So if I want to use that equation, we go Fr, and then we add this, this, and this. All the x components are coming out of that equation. You're looking at 0 plus 320 minus 240 times of I. plus. Now you're going to add all the y components. You're going to look at this, negative 200. You're going to look at this, plus 360. And you're going to look at this, which is plus 160. We're looking at negative 200. Then you're looking at positive 360. Then you're looking at positive 160. And that times of j. And the last one. So this time you're going to look at this, which is negative 480. You're going to look at this, which is another negative 480. And you're going to look at this, that's another negative 480. So what you have is you have negative 480, negative 480, negative 480 times of k. And if you go through all the actual calculations, then this is going to become 80. This is going to become 80 times the phi, 320 times the j, and negative 1440 times of k. So that's the resultant force factor, where the first number here is the x component. Then the second number here is the y component of the resultant. Then you have the third number here, that's the z component of the resultant. And all we are going to do is to find the magnitude for this and the three angles. Now, to do that, it's going to be square root, and you have the x component, which is frx, and that was 80. Do a square of that. Then we had fry, and it was 320. We square that. Then you had fry, and that was negative 1440. We do a square on that. And go through the actual calculations. This thing should be approximately equal to 1477.3 Newton. So that gives you the magnitude for the resultant force. Then your first angle, angle the force going to make with the x-axis, that's going to be cosine inverse frx divided by fr. Fr is 1477.3, frx is 80. Then you have the second angle, which is beta. That's another cosine inverse. The equation is fry over fr. This one is 1477.3, and fry is 320. Then you have the third angle, which is gamma, and you have cosine inverse, and it's going to be the same kind of equation, which is frg divided by fr. That's 1477.3 and negative 1440. And if you go through the calculations, then your first angle is 86.9. Second angle is 77.5 degrees. The third angle is 157 degrees. So, and that's all you need for the solution. You need this, that was magnitude. You need all these three angles to define the direction of the resultant force. Now, the thing to note in this particular problem is that all your forces were of type case 3. That means you had the force magnitude and you had two coordinates along those forces. So we went through this long process of finding the force vector for all those forces. So that's one point. Then the rest of the process is same, whether you have the problem in 2 dimensions or the problem in 3 dimensions. So this was all the way up here. That was step 1. That means you represented every force in its vector form. Then this part here, when you added the components, that was step 2. You took the x components of every force, added it. You did the same thing with the y components, and you did the same thing with the third component. Then things which I did here, that all will fall under step 3. So I repeat again that to add forces, whether you have problems in 2 dimensions or you have problems in 3 dimensions, it's always going to be a 3-step process. Whether you work with a plane problem